Okay, welcome to chapter 3. We will now be talking about chapter 3 of the text. And the title of chapter 3 is Pure Substances. Okay, so what's a pure substance? In thermodynamics now we're using fluids and gases as a medium inside of however we're doing thermal heat transport. If we're trying to create power from an engine, we typically use materials such as mostly fluids and liquids to help us be able to complete a process step. So for example, in your car, you would be using both gasoline as the fuel, and you would be using air as the cooling medium and the gasoline transport. And so those are the substances we would be using. So more specifically, let's talk about, so pure substances would include the following. Water is considered a pure substance. Now it doesn't have to be elemental, such as nitrogen, for example, nitrogen gas, helium. These are all, we consider these as pure substances, and CO2, for example. So our definition of pure substance means that they're not mixed with anything. It's a stable molecule, for example, H2O. In the areas that we're operating H2O, we don't expect to separate hydrogen from oxygen. And likewise for CO2, we don't expect to separate carbon from oxygen as well. And so another pure substance is air. Now that's an interesting substance because it's composed of nitrogen plus a certain amount of about 77% nitrogen and about 23% oxygen. So it's a mixture of the two. However, when we operate in the temperature range of our operation, temperature and pressure, we don't expect to separate nitrogen and oxygen. So air stays air. Also, we don't expect to, we may have phase change. For example, in water, it can go from liquid to a solid or from a liquid to a gas. And that's fine, as long as we don't have separation, but we don't separate hydrogen from oxygen. So that's what we consider pure substance. Okay, any substance that behaves in a certain way depending upon its state. So that means its temperature, pressure. And then we know that for a solid, what makes a solid? Well, a solid is composed of molecules or atoms that are bonded in a certain pattern. And those atoms are held by covalent bonds. And this can be atoms, molecules, doesn't quite matter. And then these bonds are actually, they act like little springs. So we talked about how temperature is transferred by the vibration of the molecules. So inside of a solid, these molecules never separate from each other, but they basically transfer vibration through their bonds. For a liquid, we have now clustering of molecules. There'll be a cluster there, a cluster here, and a cluster there. And these clusters will move in certain directions. And a lot of times they're held in place by secondary bonds, or actually things like van der Waals forces or ionic forces. But they're allowed, for the most part, they're allowed to move. These clusters are allowed to move freely. And then we have gas, is the last state of matter that we're talking about in this class. And that one is where all the atoms and molecules completely separate. So if this could be a nitrogen, or these could be oxygen atoms that are just completely separated, non-clustered, or they can be a combination of the carbon and oxygen, for example. So they could be molecules that don't separate amongst themselves, but then the gas molecule will separate and they all go off in different directions. All right, so these are the states of matter. And now we're going to demonstrate, so we're going to go ahead and start a new page here. We're going to demonstrate a little bit of how we use these different states of matter. Let me start off with a certain color here. Okay. So we're going to be highlighting here, this is still chapter 3-3. We're going to be highlighting phase change. Now we talked about phase change, and phase change has to do when the matter changes from within those three phases, from either from a solid to a liquid to a gas, and then it could sublimate too from a solid to a gas, and vice versa. So here we're going to demonstrate just more specifically how we use these phase changes. So we'll call this state 1. I'm going to circle it here. And we're going to be drawing some cylinders. So we have state 1, and we have a cylinder with a piston. So this would be a piston that's allowed to move up and down within the cylinder. All right, and we start off, so this is again, this piston is touching at the sides, but it's allowed to move freely without friction. And we start off with, let's go ahead, we're going to have water in here, so let me go ahead and change the color. We're going to say we have water here, that's 20 degrees C to start off with. So at 20 degrees C, and the pressure is equal to 1 atmosphere. So it's not hard to see, at 20 degrees C and 1 atmosphere, water is going to be liquid. And so we start off with liquid water. And then we're going to go ahead and apply some heat here at the bottom. And when we do that, we go to, we're going to go ahead and go to now to state 2. So now for state 2, we have the same cylinder. Excuse me. Go ahead. And now what happens is okay, bear with me please. All right, so the water inside the cylinder, now we applied heat, and now the temperature is now equal to 100 degrees of the water. So the water in here now is equal to 100 degrees C, but the pressure still remains 1 atmosphere. Now the pressure from state 1 to state 2 stays the same, because in these cylinders here, what happens is when the temperature goes up, the water here is allowed to expand, and therefore, and this is a frictionless piston, even though it may not look like it, but this is a frictionless piston inside of a cylinder, and so it is allowed to float up, basically, to compensate for the temperature rise. And therefore, because out here, I'll just use this as a, so the pressure here is equal to 1 atmosphere. The pressure surrounding the piston is 1 atmosphere, therefore the pressure inside the piston chamber is 1 atmosphere. Alright, so we still have, we haven't taken off the, again, we still have the heat at the bottom. At this point now, the heat remains here all the time, so we're heating it. Now we go to a third state, and let me go ahead and draw this piston here. And so the piston, alright, so the piston is here, And now we are still at 100 degrees, but we're starting to see something a little bit odd here. So that our temperature is equal to, let's just say a temperature here is equal to 100 degrees. And now we're getting a separation. Maybe I'm exaggerating a little too much here. But you have, so here where I draw this little triangle and where you see 100 degrees, this is here is water. But it's a special type of water. It's saturated water. And up here, you're getting a gas. And so that's vapor. But it's a special type of vapor called saturated vapor. So again, the piston, now because this vapor takes up a larger volume for the given, and it's still 100 degrees here. So it's still, everything inside the cylinder is uniform temperature. So what happens is the piston will rise and the pressure is still 1 atmosphere. So that never changes. So P is still inside the, P is equal to P atmosphere, and it's outside and inside as well because it's a frictionless piston. Okay, now we go to state 3. Okay, we are in state 3. Let's go to state 4. For state 4, let's go ahead and draw our piston. And then our piston in the cylinder. And now what happens is we have everything in here is still P is atmospheric pressure. It will always be atmospheric pressure in the cylinder. And the temperature is 100 degrees. But this is all completely 100% at this point saturated vapor. So in here is 100% saturated vapor. So there is no longer any water, as you saw in state 3. So all the water has completely vaporized to 100% saturated vapor. 100% saturated vapor. And keep in mind, we never taken off. I don't have much room here to put the flame here, but we've never taken off the flame source here at the bottom. And now, finally, we head off to our final state. This is state 5. I'm going to go ahead and draw our piston at state 5. I probably should have given myself more space here, as I'm starting to run into state 2 above. So here's our piston with the I guess the cylinder that goes on top of the piston. So now what happens is, I'm going to go ahead and change the color here. We still have 1 atmosphere pressure in here, but now we have a temperature rise, 300 degrees C. So how can that be? Well, we have 1 atmosphere pressure, and we're still applying. So we're still applying heat at the bottom here. So what happens now is, once we hit 100% saturated vapor, there is no longer any phase change. So if you look between states 2, 3, and 4, we are experiencing phase change. And if you recall, phase change is accompanied by it's a constant temperature process. So when you boil water, it stays 100 degrees C until all the water is completely vaporized. And so at state 2, we started off with 100% water. Maybe it would have been good to put right here saturated water right here. So this is state 2 was 100% saturated water. Now, state 1 was water, but it wasn't saturated. So saturated means that the temperature was taken just to the point of phase change. And then state 3 was a mixture between saturated water and saturated vapor. So we're applying heat at all times here, and that heat now is being used to change the phase. So if you remember from one of the lectures I mentioned, when you vaporize, when even water droplets that are on your skin, when they start to dry out and start to vaporize, they pull heat. And this is a constant temperature process. So this is a situation, here's an example where you actually have heat transfer from the burner here going in here, and you have a constant temperature. So this is a situation, this is phase change, so there is no delta T that's creating a phase change. It's that's creating the heat flow from here to here. It's basically the fact that it's changing phase. And now, okay, so going back to state 5, this is now the reason why this is rising in temperature now is because this is called, we no longer have phase change. We call it superheated vapor. So anything above, I shouldn't say anything, but for atmospheric pressure above 100 degrees C, the water in here is no longer water. It's superheated vapor. Well, it transitioned from 100% saturated vapor to now superheated vapor. It means that any little bit of heat will now just escalate this temperature. Okay, so these are the 5 states. Now I'm going to go ahead and map this out. For better illustration. All right, so I'm going to map this out now on a temperature versus volume. Let me go ahead and try to give myself a lot of space here. Temperature, so I'm going to go ahead and draw a y and an x axis. All right. So this is temperature in degrees Celsius, and this is volume in meters cubed. And so we had here, I'll just go ahead and draw some temperatures that we talked about. So I'm going to map out our 5 states. Here's 20, here's 100, and here's 300. So these were the 3 temperatures that we had, our 5 states. Now, for volume is kind of arbitrary here, but let's just say state 1 started here at a low volume. This is when it was all water, and I didn't really specify what. So I'm going to say that this is state 1. I'll just put a 1 here. Actually, there's a 1 there. And remember, state 2, we're going to put here at 100 degrees. So that's state 2. Actually, this is, just a second. This is not a good way to put state 1 here. Let me go ahead and erase this, sorry. All right. So we're going to put this a point, give this a point. Sorry, I didn't finish this here. Ooh. We're going to call this 1, that point 1, that point 2. So we're going to draw a straight line from 1 to 2. That signifies going from state 1 to state 2. Remember, we had water here. We heated it up till we had saturated water. And then we might maintain constant temperature to right here to point 3, state 3. And that's where we had half mixture, or a certain portion of the mixture saturated water and a certain portion of the mixture saturated vapor, where we maintain constant temperature and constant pressure. Pressure throughout this whole thing is 1 atmosphere. And then we go down to 4. And that's where we have 100% saturated vapor. And then 5 was somewhere over here. I'll just put 5 right there. State 5. And we went from... Now we started to have an increase from state 4 to state 5. We had an increase in temperature, but also an increase in volume. So at all this time, volume is changing. Is increasing. But we're going from 1, 2, 3, 4, 5. These represent our 5 states. All right, so I'm going to go with a different color now. And this represents here, go ahead and go with blue here. So this all represents P is equal to 1 atmosphere. So this line here represents P is equal to 1 atmosphere. Now, if we went and we reduced the pressure, if we were able to pull a vacuum and reduce the pressure of that piston, let's just say I'm going to change the color. Then we would have, let's just say we use P is equal to, so 1 atmosphere, we're going to say is P is equal to, we're going to say 0.1 megapascal. It's roughly about 1.1 megapascal. And so if we reduce the pressure now to P is equal to 0.01, then we're going to have a situation where this line actually starts to look something like this. So I'm going to go ahead and just go like this. Let's see. It's not coloring here for some reason. Okay. Oh man. Sorry for my drawing there. Let's try this again. So it's going to do something like this. Stop shy here, go across like that, constant temperature, and then start to climb up like that. So at 0.01 atmosphere or megapascal, sorry, this line here basically takes a dip like this. So if we were to run all 5 states within a lower pressure, and then if we were to dip even further to a lower pressure, then again it would look something like this, like that. And let's just say P is equal to 0.005 megapascal, for example. And if we were to increase the pressure, we would follow a line up here that would look like this. Let me just take this up here so there's no confusion. And then we would say this is P is equal to 1 megapascal. Instead of right below it would be 0.1 megapascal. So at 1 megapascal, it would look something like that. And again, if we keep increasing the pressure, let's just say this would be P is equal to maybe 10 megapascal. And so what you're seeing here is we're sweeping out a curve. It looks something like this. Almost like a Gaussian curve. And so this is what we call, so this curve here, so what this represents, everything outside this curve on the right side represents saturated vapor. I'm sorry, superheated vapor. I'm just going to say superheated vapor, SHV. So do you remember if we looked at this orange line, this was our primary 5 states lines. Once we pass state 4 and go to state 5, we are basically in the superheated vapor region. So anything outside of this curve, this green curve, is considered superheated vapor. Anything inside the curve is a mixture. I'm going to say mixture. A mixture of superheated, saturated vapor and saturated liquid. So let me go ahead and do something different here. So along this curve here, so I'm going to represent it with some dots here. Along the green curve, but on the curve itself, up into the very top, we call this saturated vapor. So when we land on this line, for example, state 4, that was the point there. It should be right on the line. That represents 100% saturated vapor. So if I just want to say 100%. 100% saturated vapor just on this line here. And over here on this line, so any points that land on this line up until the very apex of this green curve, that represents, I'm going to just draw it down here, this represents saturated liquid. So that would represent state or point 2, if you guys remember. I know it's kind of off the line here a little bit, but imagine point 2 being on this line here, and that would be 100% saturated vapor. So that was state 2. That's where we warm up water, and we get it to the point right before we get the first bubble. We get the first bubble of vapor to form. We are on this side of the curve. So that's saturated vapor. So everything in here is a mixture of saturated vapor, saturated liquid, and mixture of saturated vapor. So that would represent, for example, state 3, where we had a kind of a line of separation there. You can see the liquid forming, a line of liquid, and then above it a line of, right above the liquid line there is vapor. So any points in here, and this represents the majority of this curve area here, anything in here will represent a little bit of saturated liquid, a little bit of saturated vapor. And the closer you are, for example, on the orange line here, 2, 3 to 4, the closer we get to point 4, that means the more vapor we get, the more saturated vapor, and the least saturated liquid, to the point where we get to state 4, and that would be 100% saturated vapor and 0% saturated liquid. On the contrary, on state 2 was, we represent 100% saturated vapor, and we just leave a little bit away from state 2, between stage 2 and 3. We're going to get majority saturated liquid, but we start now to gain saturated vapor. Okay, so this represents we're going to see a lot of these curves in the future, whether this one's a temperature versus volume, and you're going to see how we characterize two different properties. So these are actually properties here. Temperature and volume are properties. And how this curve helps us to determine where we're at. Are we in saturated vapor space? Are we in saturated liquid space? So here is superheated vapor. So anything to the right of this green curve represents superheated vapor. So that's superheated vapor. That means super meaning we are above the saturated vapor line, and it's vapor. Now over here, anything to the left of this line, we call it. There's different ways of calling. We call it sub-cooled liquid. Another one is compressed liquid. But this is your classical. This is basically a glass of water is a subcooled liquid, which means that it's not saturated, right? Something that you would drink. It's not anywhere near being saturated. So anywhere around here is represents the subcooled compressed liquid area. And when you heat it, you get it to the point when you get to for what atmospheric pressure. When you get it to 100 degrees Celsius, you basically coincide with this saturated liquid line. At that point, all the water becomes saturated liquid. All right.